talk today about the question, what are the products of the Fenton reaction? I'll explain in a minute why the Fenton reaction is important and why we have to know what the products are and discuss the fact that there is not one product, depending on situation. Can I have the next slide? Oh, hop. Okay. In 1894, Fenton reported that when he added iron 2 salts to a mixture of tartaric acid and hydrogen peroxide, the tartaric acid was catalytically oxidized by the peroxide. Since then, the reaction of iron 2 with hydrogen peroxide is called the Fenton reaction. Let's go to the next slide, which explains why it is important. It is important because of two reasons. The red reason up is that it is claimed that the Fenton reaction is one of the main sources of oxidative stress in our body and other living systems, including plants, and that therefore we get aging, and about 70 diseases are claimed to be responsible to the Fenton reaction. I am not totally sure, I'm not a physician, that all 70 are correct. This changes all the time, but this includes cancer, Alzheimer, Parkinson, cataract, etc., etc. On the positive side, at the downside of this overhead, you can see that the Fenton reaction is used in advanced oxidation processes. Yes? To oxidize pollutants, to get rid of pollutants, which is very important. On the next slide, what happens? Can I get the next slide? Can I get the... Okay. Now, in principle, most people think that when you say Fenton reaction, the reaction is of iron 2 with H2O2, and you get iron 3, OH radicals, and OH minus. I'll discuss this in a moment. This is not definitely correct, or let's say in biological systems, I think
moi j'ai l'impression qu'on a juste additionné une fois et éliminé ça. Je pense que c'est ça. C'est pas très propre, mais ça ressemble.
Who is the competition with me? The Fenton-like reactions are reactions in which either the metal and or the water ligands are exchanged by other species, and sometimes the peroxide is exchanged by another peroxide. The first mechanism suggested for the Fenton reaction in the 30s of the last century was by Gorin and Bray, who said that the active oxidizing agent is an iron 4 complex, whereas in parallel, Haber and Weiss suggested that OH radicals are the main product, and the active intermediate, the first reaction here. If one looks at the detailed mechanism, the first look at the detailed mechanism which we did in about 30 years ago, we came to the conclusion that first of all, there is always the formation of a complex of the low valent metal ion with the peroxide. The reaction cannot be an outer sphere reaction. It has to be an inner sphere reaction. It is considerably too fast for an outer sphere reaction if one considers the Marcus theory. And now this complex of iron 2 in this case with hydrogen peroxide can decompose in 3 ways, depending on pH, depending on the components of the solution, depending on concentration, etc. The 3 mechanisms possible are, or which we thought that are possible at those days, are the formation of OH radicals, as suggested by Haber and Weiss, the formation of iron 4, as suggested by Gorin and Bray, and the direct reaction of the complex with a substrate oxidizing to give a radical and iron 3. The same radical would be produced if OH radicals react with this substrate or if iron 4 reacts with a substrate. And that's the reason that in most systems it is difficult to decide what the mechanism is. The next slide. We measured the kinetics, and if you look at the left side, most of us would say this is a good fit, but if you look at the bottom of the deviation, you see the deviations are not statistical, there is a systematic deviation, and therefore we came to the conclusion we need a second reaction. And you see that on the right side that if you put a second reaction into the 2 consecutive first order reactions, the fit is very good. On the next slide comes an explanation. The explanation is that the iron 3 formed in the first reaction reacts with hydrogen peroxide to give a complex, now not of iron 2 with peroxide, of iron 3 with peroxide, and this complex reacts with iron 2 to give iron 3 and iron 4, or iron 3 and OH radicals. We didn't know at those days. And on the next slide, we have a proof for this. We mixed iron 3 with hydrogen peroxide, and you can see that an intermediate with a spectrum is formed. This is a complex of iron 3 with hydrogen peroxide, and the claim for the kinetics that iron 2 reacts with iron 3 is on the next slide. We reacted iron 2 with methyl peroxide, but we did the same with hydrogen peroxide, and you can see the formation of the iron 3 peroxide intermediate and its decomposition, and the decomposition obeys a first order rate law, which is proportional to the rate or to the concentration of iron. On the next slide, iron 2, and therefore it is clear that the Fenton reaction occurs, or pseudo-Fenton reaction, iron 2 plus iron 3 peroxide complex. On the next slide, I show that it's not always as simple. Let's say if you take molybdenum 5 oxide and react it with hydrogen peroxide, you first form an intermediate, and this intermediate reacts with a second hydrogen peroxide to form molybdenum 6 as expected and superoxide. In this case, the first hydrogen peroxide is not enough to oxidize the molybdenum. On the next slide, we show that this is more general. In the literature, usually it says that when cobalt-2 reacts with hydrogen peroxide, it's like the Fenton reaction and you get OH radicals. If you look at this, this is an endothermic reaction and will not occur. What will occur is you'll form a complex with hydrogen peroxide as expected, and on the next slide, we did the kinetics, and 3 hydrogen peroxides react with cobalt-2 before radicals are formed. So in this case, the cobalt-2 is not oxidized at all. What happens is on the next slide, you form one hydrogen peroxide, oxidizes a second hydrogen peroxide. You form an O2 minus and bound to the complex, which is stabilized by the resonance structure showed here, and an OH from the other. This is the oxidation product, and the reduction product gives an OH radical in the system. But look what happens. The cobalt-2, which is difficult to oxidize, cobalt hexaquo, has a redox potential of plus 1.8, is not oxidized at all. All what happens is that two hydrogen peroxides bound to the same cobalt center, to the same template, oxidize one another. On the next slide, we say that this is much more general. If you have a low valent metal, it can bind several hydrogen peroxides, and there will be an oxidation of one hydrogen peroxide by another, forming a peroxyl radical bound to the metal and an OH radical. This was further shown by a Russian scientist who has shown that this happens even with aluminum and calcium, i.e. with metals which cannot be oxidized at all. On the next slide, and this is how we got into this, I was asked by a student to do something which is of environmental importance. And I saw in the literature that if you take cobalt cobalt in the presence of and add bicarbonate to a mixture of cobalt and hydrogen peroxide, you catalyze the advanced oxidation process, you catalyze the reaction of cobalt with hydrogen peroxide. Bicarbonate is a co-catalyst. And I asked myself what happens. And the answer is the cobalt carbonate complex reacts with hydrogen peroxides, forming a complex which has bound to the cobalt-2 both a peroxide and a carbonate. This complex then isomerizes to a peroxocarbonate bound to the cobalt. This now reacts with a second hydrogen peroxide, and this decomposes. Now here you don't need 3 hydrogen peroxides, only 2. And on the next slide is the decomposition. And there are 2 possibilities. You have this complex, which is on the left, and it can decompose in 2 ways. One into carbonate anion radicals, which is a reaction which is exothermic, and the other into OH radicals, which is still endothermic. This will not happen. So in this system, what happens is you oxidize the ligands. Again, one hydrogen peroxide oxidizes another peroxide and gives a peroxyl radical, and instead of OH radicals, you get carbonate anion radicals. Carbonate anion radicals are an interesting species, as you'll see in a minute, because the redox potential of carbonate to carbonate anion radical is 1.57 volts versus the normal hydrogen electron, much lower than the OH radical, and therefore it is easier to oxidize bicarbonate or carbonate than to oxidize water. On the next slide, we asked ourselves, if so, can this happen also with iron 2? Will we get carbonate ion radicals also in the oxidation of iron 2? Now, this is of major importance because in every cell in our body, there are more than 4 millimolars of bicarbonate. Under these conditions, the question is, in biological systems, do we form OH radicals as commonly assumed and commonly attributed to oxidative stress, or do we form OH, carbonate anion radicals? On the next slide, we calculated the free energy of this question. We bound a carbonate to an iron 2 and reacted it with hydrogen peroxide, forming iron 4. And the question is, how does it decompose? And you can see that the reaction to form carbonate anion radical is very exothermic. The reaction to form OH radicals is a little bit endothermic. Clearly, the chances are that you'll form carbonate anion radicals. On the next slide is a result of the experiment. Here is now a technique developed by Professor Andrea Bakak in 2012, and she said the following. She showed, or we knew, that hydroxyl radicals react with dimethyl sulfoxide to form methyl radicals. On the other hand, she has proven previously that iron 4 an oxide of iron 4 in water, I write AC because I don't know what the charges are and so on, react with dimethyl sulfoxide to form dimethyl sulfone and iron 2. She has shown at the same time that at pH 4, the Fenton reaction, below pH 4, the Fenton reaction forms OH radicals. In neutral solutions, iron 4 is formed. So here was an evidence that iron 4 is a product of the Fenton reaction in neutral reactions. This means that in the body, we don't form OH radicals. On the next slide is what happens if you add bicarbonate to the system. And you can see on the upper part of this figure something which really was not expected. First of all, bicarbonate catalyzes dramatically the rate. Even at the left part of the thing, you can see that very low concentration of bicarbonate, less than 1 millimolar, accelerates the rate by a factor of 10 or 5. But if you add more bicarbonate, the rate increases dramatically, and you get an increase by a factor of hundreds. So something dramatic happens. The odd thing is these two straight lines. I'll try to discuss them in a minute. The bottom shows that the reaction observed independent of the bicarbonate concentration, but at a constant bicarbonate reaction, is linear with the concentration of peroxide, which means we really look at the Fenton-like reaction. On the next slide, are the possible things. I'll discuss only the first set, what appears under 1. We believe that this is correct. In the paper, it is explained why the other 2 are probably wrong. And we think that what happens is that iron 2 forms a complex with hydrogen peroxide, and then at low concentration of bicarbonate reacts with this, and this forms the first order dependence on bicarbonate and the small slope. On the other hand, if you have a higher concentration of bicarbonate, remember, above 1 millimolar, which is lower than the concentration of bicarbonate in any cell we have, in the cells it's somewhere between 4 and 40 millimolar, then we form first a bicarbonate complex, and this reacts with hydrogen peroxide, and this is a larger slope. So here we have 2 things. We show that bicarbonate accelerates dramatically the rate of the reaction. The next question is, what are the products of this reaction? On the next slide, we show the NMR products in the presence and the absence of bicarbonate. The blue is in the absence of bicarbonate, and you can see that a lot of dimethylsulfone is formed. This is in fitting with Bacak's results. We form dimethylsulfone in neutral solution if there is no bicarbonate present. But if you add bicarbonate, you can see no dimethylsulfone practically is formed. On the next slide, we looked at the question, do we form by chance OH radicals? The upper part shows if you form OH radicals, you form methyl radicals, which under the conditions will form either ethane or methane. I won't discuss the ratios, but they are clear. At pH 2, where you form OH radicals, you see a lot of methane and ethane. At pH 6.1, there is a little bit. The most products are dimethylsulfone. On the other hand, if you add bicarbonate, nothing. So we don't form OH radicals, we don't form iron form. What do we form? We think that we form carbonate anion radicals, but to prove that this is the case, we wanted to show that under carbonate anion radicals, you don't form ethane and methane, and you can see that irradiation chemically, if you irradiate the dimethyl sulfoxide with OH radicals, you form a lot of ethane and methane, but if you form carbonate anion radicals, there is nothing. So I think we have proven that this is a reaction. On the next slide, we show the result for the reaction of iron 2 in acid solutions. Here we are at an acid pH 3 with excess hydrogen peroxide. And you can see that if you increase the excess or decrease the iron 2 concentration, you form more and more dimethylsulfone, which means that the reaction of iron 2 with iron 3 peroxide is a Fenton-like reaction which forms iron 4. On the next slide, we did the same thing with, instead of hydrogen peroxide, we oxidized iron 2 with peroxymonosulfate or peroxysulfate. The upper one is peroxymonosulfate, the lower one is peroxysulfate. And you can see in both systems that the NMR proves that we formed iron 4, which means that we form also in this case, which is an environmental situation, iron 4. The next slide shows that also here, when we add bicarbonate, we change dramatically. There is nearly no methane and ethane in the peroxy monosulfate. In the peroxysulfate, also when you add bicarbonate, you would get no methyl radicals. And the conclusion is that also here, the next slide, iron 2 reacts with monoperoxosulfate to give iron 4 and sulfate, and with persulfate to give the same iron 4 and sulfate. If you add bicarbonate, you get carbonate anion radicals, which means also the environmental advanced oxidation processes don't proceed via the commonly accepted mechanism. This was still not published, but was submitted for publication. On the next slide are the conclusions of this study, which tells you that the reaction of iron 2 with peroxides yields as active oxidizing agents different products under different conditions. In acid solutions, if the concentration of iron 2 is larger than that of the peroxide, not catalytic conditions, you form OH radicals. If there is an excess of peroxide, you form a mixture of OH radicals and iron 4. The ratio between them depends dramatically on the ratio of hydrogen peroxide to iron 2, which I can't discuss. If you work in neutral solution, you form iron 4 and not in the absence of bicarbonate. But if you work in a neutral solution which contains bicarbonate, which is in every living system and in every environmental system, you form carbonate anion radicals. So the Fenton reaction is dependent, and I didn't discuss here, but if I would have shown, if you put other ligands on the iron or on other metals, you change the mechanism. So there is not one mechanism. Nobody can say in general what will be the product without measuring it in a very careful system. Thank you next slide. Thank you very much for your attention, and I'm speaking from Jerusalem, so you have a picture of Jerusalem. Thank you.